First of all, the name of the class is Analog IC Design. It means I hope I can help you to get some kind of fundamental understanding how to design a good circuit on chip. All right, but with only one semester, I promise you, I cannot teach you everything. All right, because the time is too limited. So I just try my very best to help you get some kind of good but fundamental understanding. And after that, I hope you can try to learn by yourself to read papers or even textbooks. Anyway, this is myself. Yeah, an old guy, very old. Till now, I teach in the university for about 31 years. Okay, yeah. Time flies. Anyway, I try my very best. I'm the associate editors for two very important IEEE journals. The first is Transactions on VLSI Systems. In the past, TVLSI was only for digital circuit design. But when I joined to be one of the associate editors, the chief editor changed his mind to include everything. So it means everything related to VLSI, related to IC design, will be accepted for publication if the quality is good enough. So since I guess 2013 or maybe 2011, yeah. Till now, I served the journal for almost 8 years, and after that, I was also invited to a very new mega journal for IEEE. It is IEEE SS. What is the definition for mega? It means everything. Yeah, here everything for IC design, right? But here everything related to IEEE. That's it. All right, from software to hardware, from everything. Yeah, all in one. So that is the definition for mega journal. That is open access journal, the only one open access journal. What is the definition for open access? It means that you don't need to be one of the IEEE members. You can get online to download all the articles you would like to have, but only from IEEE access, because it is open to the public. But how can such kind of journal survive? After the paper is accepted, you need to pay for it. From the beginning, yeah, to my memory, $1,300 US. Yeah, it is a big money, right? More than 51,000 NT dollars. But anyway, many of the authors, they are crazy for such kind of mega journal, because the review process is much shorter than before. Yeah, we are required to finish everything, hopefully within 1 month. I mean, from the paper is submitted to the system, within 1 month, we need to make our mind whether or not to accept or reject the paper. Okay, so for associate editors, we have only 1 week to assign reviewers, and after that, the reviewers have, I guess, they still have only 1 week for review. All right, and after that, we need to make our mind whether or not to accept it. Yeah, in last year, it made a amazing achievement. We were told that for the overall publication, IEEE access got more than 10% of all the IEEE journals. Okay, How many IEEE journals? I guess more than 100. Yeah, but only one dominates more than 10%. That is IEEE SS. Anyway, why the authors crazy for that? Because for such kind of very short review process, yeah, more than often, it depends on your luck. If you are lucky, then the paper will be accepted. Yeah, unless the paper quality is really awful. Otherwise, within such kind of short period, I don't think reviewers or even the associate editors they have enough time to assess, yeah, to decide whether or not the paper is good enough for publication. All right. So luck is, yeah, it's more important than quality. Anyway, I myself never submit anything to IEEE SS, but maybe I will try, because as associate editor, I guess I don't need to pay for such kind of very expensive publication fee. Maybe, yeah. Let me think. And right now, I'm the dean of the College of Applied Sciences on our campus. Yeah. In last year or 2 years ago, I was the department chair for electronic and computer engineering. Yeah. Anyway, I served the university for quite many years, not only for a professor, but also for some kind of officers, yeah, to control, to help our colleagues. Anyway, this is totally incorrect. not double E, okay, ECE. And this is my email account, but don't contact me, all right, because I'm simply too busy. If nothing important, usually all the emails will be deleted by myself or my secretary. All right. If you have any question, if you need any help, please contact the teacher assistants. Okay. Where are the TAs? Raise your hands. TAs? Okay. And also Tony, right? Okay. Anyway, nominally we have only one TA, but I would like to help you more, especially for your homeworks. Yeah, if you are not good at IC design, I guess during the homework in the computer room, quite many students will raise their hand to ask questions. If there is only one TA, I think the process of your computer learning, yeah, your EDA tools learning will be delayed very much. So at least 2 of them will show up to help you in the computer room. Whenever we need to go to the computer room to do your homework. Yeah, and this is my website, nothing new. Yeah, anyway, I'm too busy. How about textbook? Nowadays, I think the technology evolution is quite amazing. Yeah, so everything, if you see everything online or printed, especially for anything printed, usually it means it is already out of date. Okay? For each day, I guess, thousands of papers published. Yeah. How can you keep yourself updated? Usually, you need to Google online, or you need to search through IEEE Explorer. Yeah, I think IEEE Explorer, that is the biggest database for anything related to EE or CS. Okay? So to keep yourself updated, that is the only way. To search anything online. Okay, I don't care, I don't mind, through Google Scholar or through IEEE Explorer. Anyway, that is best way for you. If you would like to read some kind of Bibles for IC design, okay, there are 2. But this is this only for you to refer. First of all, Professor Razavi, yeah, design of analog CMOS integrated circuits. Even for the second edition, it's published about 2 or 3 years ago. Yeah, And the other one, even elder one, Professor Allen. Yeah. Philip Allen, the textbook is CMOS Analog Circuit Design. Yeah, that is the third revised edition. For the third edition, it's published in 2011, but 1 year later, Professor Allen has some kind of little revision. So this is the so-called third revised edition, okay, in 2012. Yeah, anyway, that is a very brief introduction for myself and the class, okay. But for students, usually you pay more attention to the grading. Yeah, what kind of grade you will get, what kind of achievement after learning in the class you will get. Homework, at least you need to do 3 homework, and yeah, usually to the end of the semester, I will have some kind of papers for you to read and to report. Okay, so for all those homework and final project or report, will decide how much grade you will get from the class. Anyway, my promise is if you do everything I required, yeah, I wouldn't like to turn you down. Okay, you will pass at least safely. But sadly enough, yeah, I teach such kind of classes in English for till now, I think already 7 or 8 years. For each semester, never mind I taught what kind of class. There were always some students couldn't pass the class. Yeah, that is really amazing, because that is my requirement is quite low. Okay, for homeworks, you need to finish it. That's it. Never mind what kind of circuit you design. Oh, no. What kind of performance the circuit you design. Okay, only if it is functional. Even with very poor performance, you still get the minimum 70. Okay? So just try your very best. If hey, 70 is no good for you. If you would like to get 80 or even more than 90, oh, I'm more glad to offer you better grading. But you need to make it by yourself. All right? Try to design the circuit as good as possible. Then, yeah, you will get better grading. That's it. I think that is a fair deal. Not only for you, but even for my own students. If you check the gradients in the past, you can see, usually my students were not the top ones. Okay, that is a fair system. Now that is, I strongly required my teacher assistants don't do any favor to the students in my own lab. Okay, depends on not only the performance, sometimes the timing. Okay, especially for such kind of homework in the computer room, if you finish your homework the earlier, then you will get a better grading. Okay, that's it. Yeah, but even after that, we have a formal report for each homework. You still need to do a good job to hand in good enough report for your homework. That's it. All right. And then you may be curious about the content. Okay, what kind of content I would like to help you, I would like to teach you. Allow me to show you from the very beginning, the introduction to analog design. And because this is, the class is analog IC design, I have no idea and I have no time to teach you anything related to digital design. But maybe for many of you, not already that, we have the so-called digitization. We digitize everything, almost everything, when possible. It means we try humankind try our very best to make everything become digital than analog. So it means what? In theory, you had better learn something about digital design instead of analog one, right? But why? I'm still here. Yeah. Why you are here to learn something related to analog design? Anyhow, I will tell you why. Okay? That is the most important how can I say? Motivation. Okay, for myself to have such kind of brief introduction to analog design. I would like to convince you analog design is never been out of date. Yeah, it is still it is not only survive, it lives happily since after. Okay, and then maybe you already know that. What is the fundamental knowledge, fundamental background for analog IC design? Your microelectronics. Okay, you can see everything, every circuit in analog IC design originates from microelectronics. But we will have a better discussion, further discussion, and we will teach you how to enhance the performance by redesign. Okay? So it means that an analog IC design is not something from 0 to 1. No. Okay? You need to have a very good background about your microelectronics. So maybe we are already 0.5 to 1. 0.5 means maybe microelectronics is something from 0 to the middle to 0.5. And then based on your microelectronics, we can enhance your capability for better design. Then that is the purpose of the class, to enhance your capability for analog design from 0.5 to 1, hopefully. Okay? But I'm afraid that many of the students, they didn't pay good enough attention to the fundamental knowledge in microelectronics. So I myself would like to provide some kind of help. So from the very beginning, I would like to refresh your mind. That is not new, no. I think all students here already learned such kind of fundamental knowledge we call device physics, especially according to CMOS device. Okay, for such kind of very fundamental semiconductor physics, I think it's really helpful for you to get better understanding of the operation of any kind of analog circuit. Yeah, especially for Taiwanese students, usually the students pay attention to equations. Why? Because they need to do some kind of examination, test, quiz. Okay, so how to evaluate the students? I guess the easiest way is try to, test the students with such kind of equations. They need to derive a lot of messy equations. But how many transistors in a circuit you can derive? How many transistors? I think from microelectronics to my memory, the most is 3. But usually less than 2. 2 transistors. Okay? Even with only 2 transistors in the circuit, how much time you need to take for such kind of derivation? 30 minutes, maybe 20, or at least 20 minutes, 15 minutes. Okay? And how many transistors you need to deal with for your analog IC design? Usually hundreds, thousands of transistors. Can you derive anything for that? Forget about it. Okay? So what I would like to tell you is, for analog IC designers, equations always mean nothing. Okay? The understanding or what is the meaning of any equation that is the best for you. Okay? Do you need to derive it? No. Usually not. Usually not. You can ask my students. Did they ever derive any equations? I cannot say no, but very, very seldom. Okay? So the fundamental requirement for good analog IC designers is to have good understanding about the behavior of the circuit, but to get better performance, not only the circuit, but also the device. You need to have very good idea, very good sense about the device, how the device operates. Then you can try to modify them. For example, for a CMOS transistor, yeah, you know, after saturation, you will know, oh, you will get the saturation current, right? Blah, blah, blah. Anyway, for our own design, usually, you try to modify this or that, okay? You need to modify the width, the length, or the bias voltage. That's it. Yeah, that is our very boring life. Every day, every minute, every moment, you sit in front of the computer, try to modify the width, the length, the bias for your device. That's it. That is your life. Okay? But that is very good for money making. You say, hey, piece of cake. To tune the width, the length, the bias. What kind of dirty job? Oh, yeah. What you see is usually not what you get after fabrication. Okay? That is a very sad phenomenon. Yeah, they say, hey, if I double the width, then the current will be also doubled. Is it true? No. Never. It never will be true. Okay? So if you would like to only double the current, okay, only triple the voltage, is it a simple idea? No. It is really hard. I mean, to make it exactly 2.000, no. I can promise you that is some kind of mission impossible. All right? So, what you can do is to make the final result, especially after fabrication, as close to this, I mean, the ideal value as possible. That's it. But, how to make it? The better you understand the circuit, especially the device, then the closer your result will be to the ideal value. That's it. Okay? So anyway, from the very beginning, I would like to help you refresh your mind about very important semiconductor physics. And after that, I will show you again to refresh your mind about the operation principles about PN junction diode, and then go for MOS transistor, because this is the main character for analog IC. Yeah, usually more than 99.99% of the device is dominated by transistors. Okay? So, that is the main character, main device for analog chip, or even for digital chip. Anyway, okay? For CMOS chip, that is the most. So you had better, yeah, piece of cake. You learned it already, right? Right? But why? If you are good enough, you can work for Qualcomm, Broadcom, Intel. If you are not so good, you need to work for the second tier, the third tier. You can see there is a huge difference in salary, right? But why? Somebody make it. Most of them don't. Even this is the main device. If you have very good understanding about transistors, supposed to be, you can design very good circuit, right? So what is difference? not good enough understanding, and also you are not experienced enough. Okay, you need to learn almost everything. Okay, from the beginning design to the end layout. In IC design houses, I don't think, especially from the medium to large scale IC design houses, you don't need to do layout by yourself, but you still need to know, because after your design, somebody, IC layout engineers will help you to finish all the dirty work. But after fabrication, if there's anything wrong, they will put the blame on you. Why? Because you make more money than them. Okay? They just try to fit your requirement to do the layout for all the devices in your circuit. Okay? You need to tell them, you need to tell the layout engineers how to match this to that. You need to let them know which devices are critical. And they have better be surrounded by guardrail, and especially far away from the noise source, the hot source, the thermal source on your chip, blah, blah, blah. Okay, so you need to carry the most duty for the chip after fabrication. If the yield is no good, or even after fabrication, it doesn't function at all, that is your responsibility. Okay, so anyway, even in the future, most of you don't need to do layout by yourself, but you still need to have very good understanding about layout skills. All right. Anyway, after that, we can learn something from the very fundamental current sources. Why? Because for CMOS chip, usually we apply current instead of voltage for bias. Okay, that is a very important idea. Usually on CMOS chip, we don't use voltage bias. Instead, we apply current bias to modify the performance of your circuit. Okay, so you have to understand more about current instead of voltage. Yeah, but anyway, you know, for example, for resistor, you have, V equals IR, right? So they are twins. If you make your mind for the current, then you will get the voltage, right? I would like to tell you, for analog IC design, usually we focus this, and then you can derive some kind of voltage. That is some kind of byproduct, okay? But we seldom focus on voltage for bias and then get some kind of current for to be the byproduct. No. All right. So your logic thinking needs to be changed from voltage domain, because when you learn something in fundamental physics, usually voltage is the key. You decide the voltage, then the device, the circuit can help you generate how much current, blah, blah, blah. Okay? But in analog IC design, current is the key. Instead, you need to make your mind how much bias current for each block. Then you can get good enough performance. All right? Anyway, so that is the most, I cannot say fundamental, but the easiest circuit you can learn, you can design for analog chips. But even for current sources, they are still quite many. All right? It is not so simple as you can guess. And then we will focus on the fundamental building block, op-amp, operation amplifiers. You need it for almost any kind of circuit in analog domain. But how to make a good enough op-amp, that is the key idea you need to learn. Yeah, you already learned something from microelectronics. Usually for the first stage, we have single stage, two stage, or even three stage op-amp design, right? But usually for the first stage, it should be something called differential amplifier, right? So what is the major concern, major drawbacks of such kind of very simple differential amplifier? Yeah, you need to know we have the so-called VOS, input offset voltage. That is a big problem for good analog circuit. Okay? Usually we hope it is 0. No. In practice, if you don't pay good enough attention to your design and layout, how much you will get? Usually a few millivolts to more than 10. Okay? Is it harmful? You say, hey, never mention about 10. If even you focus on the minimum, 2 millivolts, is it harmful for you? Really, really harmful. Why? For example, for ADC, yeah, you have 8 bits or 10 bits, okay? 10 bits ADC. But right now, how much supply voltage you can have? It depends on the process. For very mature one, 0.80 micron, 1.8 volt. Okay? Then for 10 bits, it means what? The quantization level. I mean the LSB width. How much the LSB is. Okay? So you divide, if you apply the whole voltage to be the operation range for your ATC, usually not. Forget about it. Usually not. But in theory, you can say, hey, 100% of the supply voltage will be the operational range for your ATC. I don't care. Yeah, you can make it ideally, okay, in theory. So how much is that? Sorry. It's already 1.8 millivolts. That is less than the minimum offset. If you are lucky, yeah, if you don't pay attention to the layout and the design of your op-amp, yeah, that is the minimum you can expect. Usually, much more than this. Okay, even the minimum, even you are so lucky, you get the minimum after the fabrication. But you can see that for your not so good ADC, 10 bits right now, it's already not so good. Okay, but it still depends on the operation speed. Okay, the sampling rate, blah blah blah, power consumption, chip area. We have a lot of issues to take care of. Anyway, how about the others? Wow, if you apply better processes, yeah, for example, 90 nanometer, right? How much is the supply voltage? Usually 1.2, right? So for 65, even lower. Never mention about 7 nanometer. Yeah, the best process on earth till now. Okay, 0 point something. Anyway, even you have the same number of bits, 10. Yeah, 1 LSB means less than 1 millivolt. Okay, so such kind of offset will kill your performance for your ADC, because we have for flash ADC, okay, you have so many quantization levels. And for example, here is your input. You need to your input to all the quantization levels. Below the input, you get 1. Above it, you get 0, right? That is a very simple idea, but things will go wrong if you have such kind of huge input offset voltage. Okay? Ideally, this is the quantization level. If this is the input, higher than this, you get 1. Lower than the quantization level, you get 0. Piece of cake, right? But anyway, if the input offset voltage is positive, it means what? Even the input is above it, you still get 0 until you are higher than one of the positive offset voltage. After that, you can only get 1. On the contrary, if that is negative, yeah, for the input voltage, you increase it above the negative input offset voltage, you will get 1 already. Okay, you don't touch it. You don't need to touch it. Below it, you get 1. That is for negative VOS. On the contrary, for positive, you need to higher than that. Okay? And I told you, right now, your VOS is larger or much larger than one quantization level. So if it is positive, your input is here, you get 0. Is there, you still get 0 because VOS is much larger than your quantization levels. All right? Wow. So you need to be some levels above to get 1. Yeah. For the others, they will become 0. But for each quantization level, we have one op-amp to be the comparator. You get one comparator for each quantization level. So what is the input offset voltage? Who knows? 50% of them are negative. If you do everything correct, 50% of them are positive, 50% of them are negative. It means what? It happens randomly. Okay? So you don't expect your flash ADC will get 1 1 1 1 0 0 0. No. According to the random value of your of the input offset voltage of the comparators, yeah. During the boundary of 0 and 1, yeah, you will get something like 0 0 1 0 1 0 0 1 1 1. Okay? At the boundary, 1 and zeros will be mixed up according to the random property of the input offset voltage. So after that, please tell me, what is the real value of your input? You have no idea, right? We call it bubble. The bit bubble for such kind of phenomenon caused by input offset voltage of the op-amp. You need to solve the problem. Okay, but how? Yeah, I will tell you. Either ways. Either you try to reduce the input offset voltage, but how much you can make it? Yeah, to my understanding, right now, human kinds can make it to tens of microvolt. Okay? Wow. It's really small. But nothing is free. You need to pay for it. Pay for what? The circuit design for such kind of op-amp is really, really complicated. And usually, it consumes much larger chip area. Okay? Blah, blah, blah. So, to achieve very small input offset voltage for op-amps, you need to pay either larger circuit or higher power consumption, blah, blah, blah. Okay? You need to pay for it. Even though you can make it, maybe your boss will be really unhappy because the chip size will become so huge. Right? Chip size means money. More chip size means more money you need to pay for it. Your boss, your company need to pay for it. It doesn't make any sense sometimes. All right? So anyway, again, for analog IC designers, you need to know over design is really a bad idea. On campus, it means nothing. Okay? Yeah, because we only pay 10% of the fabrication fee. But that is for advanced chips. If you would like to apply fabrication for educational chips, your supervisor doesn't need to pay anything. Congratulations. So on campus, the students usually do over design. Okay, because to publish your paper, you need to figure out, you need to try your very best to do something better than the others. How to make it usually through over design. Okay, but this is really harmful for the companies. Again, larger chip area or higher power consumption is really bad for the company. Your company cannot compete with the others. Okay, so you need to change your mind for business. Okay, you can only do good enough design. I mean for the company, don't expect for all the circuit you are the best in the world. No, that is really dangerous. Okay? Anyway, as I told you, you can try your very best to reduce the input offset voltage, or after you get something like this, right? You need to correct the result. Because for this one, if you have an idea, you have such kind of very clear cut between the zeros and ones, right? Such kind of binary code, we call it thermometer. Okay, that is our thermal code. Thermometer. Okay, yeah, just like your thermometer, you read. Anyway, the higher temperature, yeah, you can see the red bar becomes taller. That's it. That is what's the definition for such kind of thermometer. Okay. Anyway, that is the ideal case. But in practice, you get something like this, right? So, what is the correct binary code for such kind of representation? We have the so-called digital correction. That's it. Okay? So you either make it with very good, very luxury, very precious, very expensive analog design, or with the help of digital circuit. All right? So, what is the better way? Through the help of digital circuit. Okay? So nowadays, humankind is focused very much on such kind of digitally assisted analog circuit design. It means maybe your analog circuit is not so good, but through the help of digital calibration, digital correction, you can make it much better. Good enough, I mean, good enough. In this way, you can reduce the chip size. You can reduce the power very much. Yeah, so that is a very good, very good idea for commercial design. All right? Anyway, after you know how to do a good design for op-amp, then we can go for even more complicated and the most popular IP for analog chips. Data converters, analog to digital and digital to analog. Those most important, most popular IPs for analog chips. Okay? But anyway, I would like to teach you DAC first. Why? Because usually DAC is simpler than ADC. All right? And the second reason is some of the ADC needs the help of DAC. So I need to teach you DAC first, then you can learn something about ADC with embedded DAC, right? So this is the reason. I will teach you DAC first, then ADC. And after that, the second most popular IPs for analog IC design is lock loops. Okay? Yeah. Phase lock loop, delay lock loop. They are second popular IPs. Anyway, but to make the whole church functional, you need to have some kind of a reference clock. So in between, if I have time, I will teach you something about oscillators. How to make the circuit, yeah, to get some kind of oscillation for your circuit. And then, yeah, maybe I will briefly introduce what is the applications for the log loops. Yeah, for our own design in the lab, actually, some of the circuits, they need the help of PLL or DLL. Okay, and then finally, I will have some kind of brief introduction to MEMS sensors. Yeah, MEMS is really important. Yeah, for all the smartphones. Oh yeah, here. How many sensors? From the beginning, for Apple iPhone, I heard that they embedded 9 MEMS sensors. Okay, but that is for the first generation. Right now, maybe more than 10 of them. And most of them are designed through such kind of MEMS, yeah, mechanical, electronic, microsystem. Okay, mechanical, electrical, right? Both in such kind of microsystem. So MEMS is really, really important, especially for sensor design. Yeah, but in the past, I had one class fully focusing on MEMS design for one semester. Okay, so I can have very brief introduction. What is the concept? And then I don't have time to teach you for real design. All right, only for concept review. That's it. All right, this is the whole content for this class in the whole semester. You can expect to learn. Yeah. Anyway, we can have a short break right now. So since the next hour, because I would like to teach you more, right? Usually for most of the teachers, not only on our campus, maybe if you go to NTU, go to the other good university, top universities, for the first class, teachers only have brief introduction. Then everybody can make excuse. But I think the time is really limited. So if you make your mind to attend the class, you are more than welcome. I wouldn't like to persuade you to drop the classes only if you are used to my English. Hopefully, that's it. Okay, and then I will try my very best to teach you. Okay, so after the break, I would like to have a hopefully, but not only brief but interesting review for integrated circuit, especially for analog ICs, to convince you analog IC deserve your learning. Okay, thank you.